Thanks so much for joining me once again. I hope you're all having a wonderful day wherever you are in the world. Okay, so what's today's topic? So today I want to talk about Russell's paradox. So what is that exactly? This paradox comes from Bertrand Russell in the very early part of the 20th century. So Bertrand Russell was a very prominent mathematician, a logician, a philosopher. His work was sort of the ultimate foundation of the whole notion of philosophy of language. He was also a really prominent anti-war activist and advocated against nuclear proliferation. So he was a really important thinker in the 20th century, and his thinking is still really relevant today. So Russell came along and gave this extremely powerful critique of how people had been doing set theory up until that time. So this was really important because set theory was proposed as this foundation for how all of mathematics can be defined. So what Russell was doing was he was saying, wait a minute, the way you've been doing this is wrong because it leads us into this paradoxical conclusion. So today, what I want to do is I want to look at exactly what Russell proposed. I want to give a couple of intuitive examples so we can understand the paradox in sort of simple terms. And then later on in the video, what I'm going to do is look at some proposed solutions. So some later philosophers proposed some ways to redefine set theory in such a way that it does not run into this paradox. So, okay, let's get started.
Let's imagine that we have a barber, and we'll give him a name. Let's call him Barber Dixon. Now, he lives in a small town, and by decree of the mayor of the small town, Barber Dixon is required to find all the men in the town who don't cut their own hair and serve as the barber for all and only those men. So serve as the barber for all the men who don't cut their own hair. So for example, let's say that this guy, who we'll call Jerry, he does cut his own hair, holding some scissors. So Dixon is not allowed to serve him because Dixon can only serve the men who don't cut their own hair. Then let's say there's a second guy, George, who doesn't cut his own hair. So by the mayoral decree, Dixon has to serve this guy because he has to serve all the people in the town who don't cut their own hair. So this guy, George, he doesn't cut his own hair, and this guy, Jerry, he does cut his own hair. Okay, so here comes the paradoxical question. The question is Barber Dixon permitted to cut his own hair? Now let's think about it for a second, and we'll start to see why the paradox emerges. So if Dixon does cut his own hair, then he is breaking the law. Why? Because he is only allowed to serve customers that don't cut their own hair, right? That's the nature of the decree. He's only allowed to serve customers who don't cut their own hair. So if he is serving himself, he's breaking that rule. Okay, well, what about on the other hand, if he doesn't cut his own hair? Is that permitted? Well, no. If Dixon doesn't cut his own hair, then he's also breaking the law. And why is that? Because the mayoral decree says that Dixon must cut his own hair because he has to serve anyone who doesn't cut their own hair. So we're in a sort of damned if you do and damned if you don't situation. So if he's serving himself, he's breaking the rule that he's only allowed to serve customers that don't cut their own hair. And if he doesn't serve himself, then he is missing a customer because he's required by the decree to serve everyone who doesn't cut their own hair. So in a way, he's damned if he does and damned if he doesn't. So this is a version of Russell's paradox. And the paradox emerges when we try to carve out the set of things that are reflexive, so the things that sort of operate on themselves, versus the set of things that aren't reflexive, so the things that don't operate on themselves. Now, it just takes a little bit of abstract thinking to shift this paradox from the world of barbers and hair cutting to the world of set theory. So to translate this paradox from the world of barbers to the world of set theory, all we need to do is replace, the notion of man in this world, so these three guys, with the notion of set, and the notion of cutting hair with the notion of contain. So instead of talking about men who cut their own hair, we're talking about sets which contain themselves or sets which don't contain themselves. So let's look at another example, which is closer to the set theoretic definition of the paradox. So you might have visited Wikipedia at some point in your life, and you might have seen these pages which are lists of articles. So we see things like the list of compositions by Johann Sebastian Bach, or the list of Dune secondary characters. Okay, so what if we had a Wikipedia article which was lists which contain themselves? And then conversely, we also had the article lists which don't contain themselves. Now, these aren't real lists on Wikipedia. This is just for the sake of argument. So what kind of things would we find in these two lists? So for example, let's say there's an article lists which start with the letter L. So this list would contain itself because it itself starts with the letter L. So it would be an element of lists which contain themselves. On the other hand, something like lists of MCU characters, the list itself is not an MCU character, so this would be a member of lists which don't contain themselves. So here's where the paradox comes in. Would the article lists which don't contain themselves, would this article list itself as a member, in the same way that lists which start with the letter L lists itself? So if we start to think about it, this is where the paradox comes in. So if this article, lists which don't contain themselves, did list itself as a member, this would be a mistake. And why would it be a mistake? Because in that case, the list would contain itself, and it would go against its own rule for inclusion that the list doesn't contain itself. So that would be a mistake. But on the other hand, if it didn't list itself, then it would also be a mistake, because in that case, it would be missing a really important entry. It would be missing itself. And if we sort of impose the fictitious rule that these Wikipedia lists have to contain all and every article which falls into this category, then this would be making a mistake, right? Because it's leaving a particular entry out. So we're in a paradox. We're in a damned if you do and damned if you don't situation. So let's look at the formal definition of Russell's paradox. So here is the formal definition of Russell's paradox. So let's say X is a set, and it's a special type of set. It's a set of sets. So X is the set of sets S, right? And to be a member of the set, you need to meet the following condition: that the set S is not a member of itself. This correlates to the customer who doesn't cut his own hair, or the Wikipedia list which doesn't contain itself. So X is the set of sets which don't contain themselves. Then we want to think, is X a member of itself, right? What is the condition on which X is contained within itself? Okay, so if X is in X, if X is in itself, then X has to meet the condition which is set here, right? So for X to be in this set, then it needs to not be in this set. If you've never seen this symbol before, this double-headed arrow, this means if and only if. So if with two F's, meaning if and only if. So what that means is that these two conditions, the two sentences on either side of the arrow, they have to be true at the same time, or they have to be false at the same time. There's no possible scenario in which one is true and one is false. That's what the double-headed arrow means. So we can see sort of immediately that this is a paradox, because X is in X is true precisely when X is not in X is false, and X is not in X is true precisely in the cases when X is in X is false. As these two sentences are negations of each other, they can't possibly be true at the same time or false at the same time. It's actually impossible for them to be true at the same time or false at the same time. So this is how we're getting into a paradox. Because once we have this condition, then we are forced into this false conclusion, this conclusion which is always false. So this is obviously a big problem, that we are asserting this premise here, right? And nothing in our theory so far is preventing us from constructing this premise, but the premise is leading us into a false conclusion. So this is Russell's paradox, and this is why this idea was so important, because it's showing that our sort of reasonable standard assumptions of set theory, they're forcing us into this position where we have to conclude this absurd conclusion, this conclusion which could never be true. Okay, let's look at an example problem. Some English adjectives are descriptive of themselves. For example, the word polysyllabic is polysyllabic. Now, if you have never seen the word polysyllabic before, polysyllabic means it has many syllables, right? So poly means many, like Polynesia, many islands, and then syllabic means syllable. So polysyllabic is itself polysyllabic, right? Because we have polysyllabic. So it has 1, 2, 3, 4, 5 syllables, so it's polysyllabic. Okay, so some adjectives are descriptive of themselves, whereas others are not. For instance, the word monosyllabic is not monosyllabic. Monosyllabic is the opposite of polysyllabic. Monosyllabic means one syllable. Mono means one. Yeah, right, so we got monosyllabic. So monosyllabic is not monosyllabic. Okay, so we're sort of seeing Russell's paradox show up again, but instead of the domains of sets, this is in the domains of adjectives which refer to themselves. So in this instance, polysyllabic does refer to itself, but monosyllabic does not. Okay, the word heterological refers to an adjective that does not describe itself. Okay, I personally have never heard of this word before, but hetero means different. I'm assuming that this means that the form of the adjective and the meaning of the adjective are different. So is heterological heterological? Explain your answer. Okay, so what we've done here is we've got this arrow, which means, self-describing. So this arrow here, this means that something is not self-describing. So let's have a look at heterological and try to decide if it's self-describing or not self-describing. Okay, so what's our word? Okay, so let's try to think about whether heterological is heterological. So if we assumed that heterological did describe itself, so it was self-describing, we would immediately run into an error, right? Because the meaning of heterological is it's not self-describing. So if it was self-describing, then it would be a violation of the definition we set forth, the definition we set out of the meaning of heterological. So the meaning of heterological is that it's not self-describing. So if we said it was self-describing, then we would be violating that condition. Okay, so that one didn't work. So let's say no. Okay, so let's assume on the other hand that it is not self-describing. We would meet this condition, right? Because we're not self-describing. So if we assumed that heterological was not self-describing, we would still be in the paradox because the definition of heterological is not self-describing. So if we said it indeed was not self-describing, then it is just self-describing. So we're forced into a position of saying that heterological is self-describing. So this is just another case of Russell's paradox, a sort of damned if you do, damned if you don't kind of scenario, where we can't decide really whether the word heterological is self-describing or is not self-describing. Both of those seem like impractical options. Okay, so let's now look at some proposed solutions to Russell's paradox. So if you remember from a previous slide, that if we make this assumption here, then we're forced into this paradoxical conclusion, this conclusion which is always false, that x is in x just in case x is not in x. So the approaches to solving Russell's paradox really focus on this part of the conditional, mainly in terms of making this expression badly formed. So making this expression something that we cannot write down in a well-formed set theory. So the first solution I want to look at is from these two. So this is Zermelo, and I might be pronouncing these wrong. This is Fraenkel. So I'm just going to give you a general overview of their approach to the problem. So basically what they said is that the expression S, the set of sets S such that S is not a member of S. So their central proposal was that this part of the equation is badly formed because we can't just say something unrestricted, the set of sets such that. We can't just say the set of X such that. We need to follow the convention, and it's a convention we've been using in our set builder notation in these videos. We have to follow the convention that we have to say X is a member of some set. So for example, let's say X is a member of the set of integers such that, X is greater than 3 or something like that, right? So we can't just simply say X such that X is greater than 3. We can only use the set builder notation where we're taking the elements of our set from a bigger set, right? Just like we have here. Okay, so how does that help us with Russell's paradox? So let's have a look. Okay, so given that we can no longer construct sets in this way with this unconstrained S such that, we have to say S is a member of some bigger set. So let's just call this set A, because we have to fulfill this condition that the members of the set we're constructing come from a bigger set. So S is a member of A such that, and then we've got our condition, S is not a self-containing member. S doesn't contain itself. Okay, so let's see how that changed things. So all we're doing is we're replacing this part of the conditional here. So let me just scroll down a bit. Let's rewrite it out. So let X equal the set of sets in some bigger set A. So it's the only thing we're adding. We're only adding this. Now, again, we still have the same question as Russell did. Can X be a member of this set? Does this set here, contain itself? Okay, so X is a member of X just in case. So now we're coming to a point where the two versions of this conditional, Russell's version and the Zermelo-Fraenkel version, are starting to become different. Because if we remember Russell's version, X is a member of X just in case it meets this condition, right? That it contains itself. And that's the only condition it needs to meet to be a member of this set. But in this version of the theory, we actually have two conditions you need to meet. So to be inside the set, you need to meet the condition on entry, so that S doesn't contain itself, but you also need to meet the condition that you are a member of the bigger set A. Okay, so let's write that down. So X is in X, so X is a member of this set, just in case it meets the set entry condition, right? So far, same as Russell. And we also have this condition here now as well. So X is in A. Okay, now, just with the addition of this component, this expression here is no longer a contradiction. I'm just going to write it out with a bit more space. So we've got X is in, and so I'm just rewriting this expression here. X is in X, if and only if X is not in X, and x is in A. Okay, and then there's brackets around here. Okay, so this is the expression. We are trying to show that this is not a contradiction. There is a situation where it is true. Okay, so let's try and think about when this sentence would be true with this double-headed arrow. So remember I said earlier that a double-headed arrow means the thing on the left and the thing on the right have to be true at the same time, or they have to be false at the same time. Now, we can immediately eliminate the possibility that these could be true at the same time, right? It's not possible for these to be true at the same time. Why? Because we have x is in x here on this side, and x is not in x here on that side. But they can be false at the same time. So let's try and examine what a situation would look like where the two expressions on either side of the double-headed arrow are false. So let's look at the negations of both of the expressions. So the negation of this expression is x is not in x. And then the negation of this expression would just be, well, let's just put a not outside of it. So x is not in x and x is in A. Okay. And we're looking at this situation where both of these expressions are false at the same time. So we're going to connect these with an and. Okay, so this is a situation where both conditions on either side of the conditional are false. Okay, so we want to simplify this. So let's keep the left side of the conjunction intact. So x is not in x, and we didn't do anything to that side. But now we're going to apply De Morgan's rule to this side. So you'll notice that we've got the negation of a conjunction, and De Morgan's rule tells us that the negation of a conjunction is equivalent to the disjunction of the negations. Okay, so we want first the negation of this expression here. So x is not in x, so the negation of that is x is in x. X is in x. And then in De Morgan's rule, the and changes to an or. And then we want the negation of this part. So x is in A, the negation is x is not in A. Okay? And then we should put some brackets around this one. Okay, so if we look closely at this formula, what we can see is this expression here is the negation of this expression here. So what we're essentially doing is we've got P and not P or Q, right? I'm just putting these expressions into very simple terms. So when we have this kind of situation, so we're asserting two things are true. We're asserting P and we're asserting not P or Q. On this side of the assertion, we have two options, right? We have not P and we have Q, and we can choose either option without any problem. So because we are already committed to assuming P, we are not allowed to assume not P anymore. This option is now closed to us. The only possible option we're allowed is Q. Okay, so let's go back to our formula. So we are forced to still assume x is not in x, and now we can no longer assume this part anymore because x is in x is a negation of something we've already assumed. All we can assume is this option here. So okay, so we've reached a sort of very simple conclusion here. X is not in X and X is not in A. So X does not contain itself, and furthermore, it is not in A. So let's just scroll up and look at our paradox again. Okay, so we can see now that this is not a paradox anymore. If we assume that X equals the set of sets S such that S comes from A, such that S is not a member of itself, then we assume this biconditional here. And if we assume that, we are forced into assuming one conclusion, namely, both sides of the biconditional are false, and we have just done the calculations that we can simplify this to, and I'm just reproducing what I've written down below, X is not a member of itself, and X is not a member of A. So this is not a paradox at all. This is actually a very straightforward kind of proposition, right? So let X be the set of sets such that S is in A and S doesn't contain itself. Then X cannot be a member of itself, and X is not a member of A. Nothing paradoxical there, nothing contradictory. We have defined sets in such a way that we have avoided Russell's paradox. Okay, let's look at a different solution to the puzzle. So here's the paradox again. Now, like the last solution we looked at, this solution focuses on making this expression that I've just underlined, making this expression an impossible thing to write down. In this particular solution, what it targets is this part here. It says we cannot write an expression of the form S is a member or S is not a member of S. So this solution comes from the philosopher Quine. So this is Quine. And it's a theory of types, or type theory. Now, if you have ever studied any kind of computer science, any kind of software engineering or programming, you will most likely be familiar with some version of type theory. So for example, if you have ever programmed in Java, now if you haven't, don't worry too much about this, but if you've ever programmed in Java, you might know that if we want to create an object which is an array of integers, we might write something like array list integer, right? So something like, I don't know, 1, 2, 3. But if we wanted to create a list of lists of integers, we would have to write array list integer. To have a list of lists of integers, something like this, where we've got a list of 2 items and the 2 items are themselves lists of integers. Okay, but the key thing about type theory, and this is why type theory has been so influential in computer science, is that these two things, a list of integers and a list of integers, are not the same. They are 2 different types. Okay, so this was Quine's idea basically. So what Russell said is all objects in set theory have types. Okay, and things that aren't sets, for example, the number 3, this smiley face, the word hello. So these things aren't sets, right? These have the type, and I'll write the type in blue, these have the type 0. So Quine's idea was that an object of type n greater than 0 is a set of objects type n minus 1, right? So an object of a type n, where n is a number greater than 0, is a set of objects of type n minus 1. So let's scroll down and look at a couple of examples. So, okay, so we've already seen that the number 3, the smiley face, and the word hello are type 0. So the set containing objects of type 0, so for example, this set containing 3, 4, 5, the type of this would be type 1. Why? Because an object of type n, so n greater than 0, so like 1, an object of type 1 is a set of objects of type n minus 1. So n minus 1 is 0. So an object of type 1 should be a set of objects of type 0. Okay, what would a set of type 2 be? Well, a set of type 2 would be a set of sets of type 1. So for example, something like this, 3, 4, 5, I don't know, 6, 7, 8. Okay, so we know that these component elements of this set are type 1, right? So a set of those objects would be type 2. Okay, so where does this get us with Russell's paradox? Let's scroll down a bit. So what it means is that if we have an expression A is a member of B, or A is not a member of B, then A must be of type n minus 1, and B must be of type n. A must be of type n minus 1 and B must be of type n. And why is that? Because we know that an object of type n contains objects of type n minus 1. So scrolling up back to Russell's paradox, basically the idea is that we can never write an expression like this, where S is a member or S is not a member of S. Because if S and S are the same thing, if S and S are the same thing, then their types will be the same, right? This type will be n and this type will be n if they're the same object. So this goes against Quine's rule, which says, so something can only be an element of type n if it's itself n minus 1. So basically what that's saying is that this expression here is badly formed. So it doesn't matter if it reaches a paradoxical conclusion because we're never going to assume this premise because it's not a possible premise of Quine's version of set theory. So that's Quine's solution to Russell's paradox, stated very briefly.
Okay, so we looked at a lot today. So we looked at Russell's paradox. We looked at a couple of intuitive examples of Russell's paradox, like the Barber example and this example with the Wikipedia lists. And we looked at some proposed solutions to the paradox. So there's a lot of really influential ideas there, some ideas which have really shaped the way we think about set theory and mathematical philosophy in general. So let me know in the comments if you got any questions. And thank you once again so much for joining me. Please remember to like and subscribe, leave a comment, and I will see you next time. Bye, everybody.